With this background on the HMM, let's see the three problems we want to address in HMMs. First one is an inference problem. Given an observation sequence and an HMM, determine the most possible hidden state sequence. And in the likelihood problem, determine the overall likelihood of an observation sequence X being generated by the HMM. While in the training, we have to find the best parameters for HMM for the given data. Let's first discuss about the inference problem. Let's understand the inference problem using the POS sequential learning problem and consider the example, the dog barks. Given this sequence, we have to find the underlying hidden state sequence which generated this sequence. This is the trellis diagram of HMM where the states are indicated here, and while going from left to right, and this indicates the instances of sequence 1, 2, and 3. For the given sentence dog barks, we have to find the best possible sequence state it generated. To do it efficiently in HMMs, we have to do this one efficiently in the HMMs. If we do in a brute force way, there are like 27 possible sequences paths are possible. Since there are 3 states and the sequence length is n, there are 27 possible possible paths are possible. So in order to do it efficiently, what we use in HMM is a Viterbi decoding, which is popularly known as a dynamic programming. So in order to compute, in order to perform the inference, first let's define deltas here. The initial delta S of 1 is the probability of starting in the state S and emitting the symbol x1 in the first position. This is indicated by this is computed by initial probability and emission probability of being in a state S and emitting the word x1. So this is how the deltas are computed in the first instance, and in the subsequent instances, we can make use of recursive solution to compute this. This is possible because of the Markovian assumption we made, where the current state is independent only on the previous state, and the current state is dependent only on the previous state and independent on all the previous other states. So by making use of the Markovian assumption, we can rewrite deltas in terms of previous deltas and the transition probabilities from that particular state to the current state, and also the emission probability of being in the state SM and emitting the symbol XT. And in order to decode the sequence, best possible sequence, similar to the backtracking pointer in dynamic programming, here we use sigma to backtrack the best possible state sequence, which is the argmax or SL, which keeps track of what is the best possible previous state. Let's try to understand this with an example. Let's try to decode the hidden state for the example which we considered, the dog barks. Let's say if you want to compute delta for the delta 2 at the second sequence instance, and for the word dog, delta noun of 2, which is indicated by delta noun of 2, represents the probability of reaching the state noun and emitting the symbol dog. And we need to find what is the best possible path out of these 3 to reach this particular state. In order to compute that, first let's see the possibility of coming from determiner state and in that state emitting the symbol the. So this is computed by pi det into multiplied by emission probability of the word the being in the state determiner. And in order to compute the path, we have to multiply with the transition probability. After multiplying with the transition probability, uh, uh, and then reaching the state noun and emptying the symbol dog, which is indicated by emission probability of b noun comma dog. This is the first term, and we have to compute all possible paths. So the other possibility is reaching from the state noun to noun by and while in the previous state emitting the symbol the. So this is represented by this particular term being in the initial probability, the previous delta noun into transition probability and the emission probability here. Similarly, we can uh, compute uh, the path associated with verb to noun using this equation. So out of these three, we have to find the best possible path. So let's consider the previous values and substitute the values here. So these are the values. Recall that the observation, the emission probability of the word the being in the state noun is 0, and also the emission probability of the word the being in the state verb is also 0. So in this expression, these two terms will become 0, and the argmax of the previous term in the back pointing tracking variable will goes to determiner, since the observation probabilities of these two terms are 0. Similarly, we have to compute the deltas for all possible states in all sequences using the recursive approach. And after reaching the final instance of the sequence, we can find the argmax of the deltas which we computed. In this case, it turns out that the last tag, which is the most likely tag, is a verb, and uh, and uh, and after obtaining this, try to find what is the previous best path, and going further backward, we can decode the whole possible state sequence. So this is the inference algorithm in Viterbi. This is similar to what you might have already familiar with the dynamic programming. And the second problem is the likelihood computation problem. Here the goal is to determine the likelihood of the data p theta of x1 given up to so on, given the observation sequence x1 to xn. Since we don't know the likelihood, since we don't have access to the hidden states, we have to marginalize it over all possible hidden state sequence. Summing over all possible state sequence could result in computationally expensive. So let's consider the HMM with n states and length of observation is t. Let's consider this case. In this case, the possible number of computations involved here is order of t into n power t. By making use of the Markovian assumption, we do not have to explicitly compute each possible path, but we can make use of Markovian assumption and then do it efficiently. This one such algorithm is forward algorithm, which results in a reduction in the computational accuracy, which is of order of t n square. Let's see what is forward algorithm. In forward algorithm, the probability of observing the observation sequence x1 to xt and being in the state s at time t is given by alpha s of t, which is the probability of uh, observing the sequence x1 to xt, and the hidden and at the teeth instant the hidden state is s. Uh, let's initialize this alphas in the first state as the probability of starting the state sequence with a particular state as is computed as initial probability of being in that state s and emitting the symbol x1, in emitting the symbol x1, probability of emitting the symbol x1 in the state s. This is similar to what we have seen in what we have observed in computing the inference problem using deltas. Uh, similarly, uh, similarly for uh, uh, similarly for alpha s one of t, from the initial state to the successive states, we can make use of the recursive solution, recursive approach by the previous alphas and then compute it efficiently rather than enumerating each sequence. Compute the probabilities recursively using the Markovian assumption. That's the idea here. This is very similar to the deltas which you computed in inference algorithm, but the only change is that there we use the max operator to obtain the best possible path, while here we perform summation to marginalize over all possible state sequences. The likelihood of the data is computed by computing the alphas of the final sequence instance and then summing it over all possible states. Similar to the forward probabilities, we can compute the backward probabilities the using betas. These are further used in HMM training to find the parameters. To estimate the state occupancy probabilities, betas are utilized over there. We can see it in the later part. So let's try to define the beta and then try to understand how we can also compute the likelihood using beta. The beta indicates the probability of future observations given that HMM is in state S at time t. Similar to forward probabilities, we can also compute backward probabilities uh, uh, starting from the backwards and then coming towards the left side. So we can initialize it with beta s of t, which indicates the final probability, which is equal to 1, and then let's integrate the and then for beta t minus 1 is computed recursively using future betas and the transition probabilities and the observations in the future states. We can also compute likelihood using the backward probabilities using this equation, which is a summation over all possible betas in the initial state and the initial state probability metric, probability values, and the corresponding emission probabilities. So far we discussed about inference and likelihood problem, and next we will discuss about the training HMM using training HMM parameters and obtain the parameters of the HMM. Based upon the availability of the labeled data, we can train HMM in two approaches. If the entire training data is labeled, then we can perform supervised training. But when the huge amount of data is unlabeled, then we have to go for semi-supervised modeling. Let's first consider the supervised approach. In supervised training, we have access to the labeled data. So the input sequence is associated with the corresponding state sequence. Recall that joint distribution is expressed in the form of mark in this form by factorizing it in terms of initial probability and transition probabilities and then emission probabilities. We can rewrite this expression since the labeled data is available, we can rewrite this expression in terms of model parameters. If if we rewrite this expression, these are the initial probabilities, and uh, p of p of x given p of y given yt given yt minus 1 is the transition probabilities, which are represented by as a asl comma sm indicates the state transition from sl to sm, and cas sl comma sm indicates the number of transition from state sl to sm, and bj's are the emission probabilities, and cb indicates the number of emissions of the word vk from the state sj. So for simplicity, ignore this term and try to estimate the parameters of A's and B's, and by considering this term. Recall that A's and B's are the transition and emission probabilities, and these and they should sum up to 1. So for each SL, the transition probabilities summing over all possible reachable future states should sum up to 1, and similarly within each state, the emission probabilities summation over all possible watts should sum up to 1. So these are the constraints used to solve the objective function. So for each state, different optimization functions are defined for both transition and emission parameters. For transition parameters, this is the objective function, log of the product of the terms involved with transition parameters and the corresponding counts using the constraint over the transition parameters. And similarly, for emission parameters, we can define the objective function and the constraint over the transition over the emission parameters. So these are solved using Lagrange multipliers. So using the Lagrange multipliers, we can introduce a Lagrange variable and then and try to maximize this particular objective function for transition parameters, and the corresponding expression for the emission parameters is this one. So these are the parameters of A's and betas can be obtained by differentiating and equating these objective functions to 0. We can differentiating the terms and equating to 0 will give us this one. In this objective function, we have to differentiate with respect to a sl comma sm, which are the transition parameters which we are interested to estimate. So in this particular summation, there is only one term which will be dependent on ASL comma SM. Similarly here, so differentiating with respect to the ASL comma SM will result in CA divided by ASL comma SM plus this factor, this turns out to be lambda A. So these are the expressions. These are the expressions for the solution for transition and emission parameters. While lambda A and lambda B are the Lagrange multiplier parameters which are unknown. Let's try to estimate these parameters. Rearranging the terms by moving the lambda to RHS and then summing it over all possible states. We know this term is 1, and which implies that lambda equal to summation over Sm of the counts of this equation. Similarly, for rearranging the terms and solving for lambda b results in this expression. Once we get the lambdas, we can go back and substitute in this equation to find the transition parameters and beta parameters. So these are the expressions. These are the final estimate of the parameters by solving the Lagrange, by solving the objective function using Lagrange multipliers using the constraints. We arrive at these estimates for transition and emission parameters. Let's understand what this mean in terms of words. So the transition parameters A theta SL comma SM indicates the number of transitions from state SL to SM divided by the total number of counts of state SL. Similarly, the probability of emitting a word Vk from state Sa is given by B Sa comma Vk, which are number of emissions from the word Vk from the state Sa, and the number of total counts of state Sa. And these are fairly intuitive. Yeah. These are the solutions we arrive at for supervised learning. Let's see how to do for semi-supervised learning. Let's say some data is labeled. Then we can estimate the initial